This week we're going to talk a lot about acidity. I know you've talked a little bit about acidity if you've taken general chemistry here. Those of you that have taken analytical chemistry have spent a little bit more time on it. I want to back off of that because what I care about when it comes to acidity is very, very different than what you focused on in those classes. So you're not really going to need a calculator here, so put them down. First thing we got to talk about is the difference between pKa and pH. One of them I care about a lot in this class. The other one, much, much less. So pH is the negative log of the concentration of hydronium ion, H3O+, whereas pKa is the negative log of this Ka, which is an equilibrium constant for acid dissociation. It's essentially how much of that acid Ha is giving up a proton to water and how much of it is just staying unionized. So pH is very concentration dependent. If I make 1 molar solution of HCl, that's pH 1. If I make a 0.01 molar solution, pH 2, etc. So again, the pH changes as the concentration of acid changes, because that's just what pH is. It's measuring how much H3O+ you have in the system. However, this is an equilibrium constant. So this is going to be dependent on the molecule. It's also dependent on the temperature and solvent. We're going to kind of forget about that most of the time, but it is true all the time. But it's dependent on the molecule. So if I ask you, what is the pH of acetic acid? That's not a real question, right? Because it depends on how concentrated the acetic acid is. Am I talking about like absolutely pure acetic acid? Am I talking about vinegar in my kitchen? Am I talking about balsamic? Whatever, right? Asking me what the pH of a molecule is not legitimate. Asking me what the pKa of a molecule is super legit. If you ask me what's the pKa of acetic acid, I'd say it's about 4.75. Do I expect you to memorize that number? No, I don't. I'll give you some rough numbers to know later on. But long story short, I can talk about pKa as being dependent on a molecule and not dependent on concentration. But much like pH, lower pKa's mean stronger acidity. So in this case, a stronger acid. And when we say strong acid in this context, most of our acids are not going to be as strong as HCl, where they fully dissociate. Almost all carbon acids are going to be quite a bit less acidic than that. Again, here in organic chemistry, we're not just concerned with learning stuff. We want to be able to use stuff. So how can I use pKa's to predict equilibria and equilibrium constants without a calculator? Put your calculator down. Here is our first equilibrium of Chem 250. Good times. Check out the arrow here. Notice that this is not a double-headed arrow like that. That means something entirely different that we're going to get to in some number of weeks. So don't draw that. 2 arrows, 2 fishhook arrows, or I guess regular arrows, either way. 2 arrows pointing opposite directions. Equilibrium. So you see Na, means sodium. So sodium forms ionic solids. So whenever you see an Na in a molecule like this, or a K or an Li, anything from that first column of the periodic table, I want you to automatically remember that it's actually Na+, and whatever it's bound to is minus. What I have here then is OH3- and this NH3, and they're in equilibrium with this NH2- and this CH3OH. So take a second and look at what is actually happening in this reaction. What is actually happening is that this NH3 is going to NH2, is losing a proton, and this thing is gaining a proton. So we have words for that. Our words for that are acid and base, right? So this is an acid in this context, and this is a base in this context. Note I said in this context, NH3 is not always an acid. In fact, NH3 is very rarely an acid. NH3 is actually a pretty good base most of the time, but not here, right? These words are defined by what they're actually doing in the reaction. So NH3 is actually giving up a proton to go to NH2+. And so in here, if nowhere else, this is an acid. I should pause here for a quick vocab lesson. When I say acid and base here, I am using them in the Bronsted sense. Bronsted acid is a proton H+ donor, and Bronsted base is a proton acceptor. That's what's happening here. This is giving up an H+ to give me a negatively charged amide ion, and this is taking a proton to get neutral. So that's Bronsted acid, Bronsted base. Lewis acids and Lewis bases, the concept is a little bit different. Lewis acid is something that's an electron acceptor. The Lewis base is something that's an electron donor. We're going to think about these quite a bit later on when it comes to actual reactivity. And we're going to rename them. This is going to be an electrophile, and this is going to be a nucleophile. But that's coming later. For now, when we talk about acids and bases, we're talking about them in the Bronsted sense. Acids, proton donors, bases, proton acceptors. Okay, I've redrawn my equilibrium here. To solve this, to figure out what the equilibrium constant is, I need to know the pKa's for my acids. And again, these are molecule specific, not concentration specific. So how do I know what the pKa of NH3 is? Well, I'd probably go look it up. This is something you can look up in a book or on Wikipedia. I happen to know that the pKa for NH3 is about 33. What's the pKa of this thing? This is an alcohol. This is methanol. The pKa of this turns out to be about 15. Which is the stronger acid? Stronger acid has the lower pKa. So this one is the stronger acid. We should bring up an important concept here, the conjugate acid and conjugate base. So we think about these things as pairs. So we said before that in this reaction, NH3 is acting as an acid. Its conjugate base on the other side of the equilibrium, once it's given up a proton, its conjugate base is this NH2 minus. So, and if this NH2 minus, its conjugate acid is NH3. So these things are a conjugate acid-base pair, just as these two are a conjugate acid-base pair. When this thing loses a proton, it goes to its conjugate base. When this thing gains a proton, it goes to its conjugate acid. Strong acids have weak, stable conjugate bases. By weak and stable, I mean the same thing, low in potential energy. If a molecule is low in potential energy, especially if the charge is low in potential energy, then it's going to not want to react, right? That's what I mean by stable. Things that are low in potential energy are stable. They are more unreactive. Okay? We can also flip this around. Strong bases tend to have weak, stable conjugate acids, right? So here, this is a pretty, let's say here, this is a really, really weak acid. Okay, as I said, the pKa is a pretty high number. If this is a weak acid, that means that its conjugate acid, weak acid has a strong conjugate base. A weak acid has a strong conjugate base. And we can flip that around here. If I have the stronger acid here, that means I've got the weaker base here. And so, which side of this equilibrium will be favored? The strong acid or the weak acid? Well, again, nature wants to roll down the hill and get more stable. And so this equilibrium is going to favor this side. All right? Nature favors going from strong acid to weak acid. Right? That's why if I pour acid on something, it doesn't get more acidic, right? It gets less acidic as it chews up and starts a fire or whatever. I did promise that we would actually calculate the Ka for this reaction, the equilibrium constant, and we would do so without benefit of a calculator. So here we go. One last time, here's our equation. OCH3 minus and NH3 in equilibrium with methanol, OCH3, and NH2 minus. So if I want to find the equilibrium constant, you won't actually have to do this math too often. I'm just doing a quick derivation here. If I want to find the Ka here, I just take the concentrations of the products divided by the concentration of the reactants. If I actually plug it in, and I'll leave this as an exercise for the viewer, this actually turns out to be just the ratio of the two Kas. This is the Ka of NH3, which again would be NH2 minus times H3O plus divided by NH3, divided by the Ka for methanol, CH3OH. And if I said the pKa for NH3 is 33, what that means is that the Ka is 10 to the negative 33. This Ka would be 10 to the negative 15. And if you subtract that, if I do my 8th grade math, and I have an 8th grader, so my 8th grade math is top shape right now. Ka turns out to be this, 10 to the negative 18, which as a number, numberly speaking, is small. Right? It's very, very close to 0. Reactants favored. If I mix this compound, if I mix sodium methoxide and ammonia, am I going to have any NH2 minus? No, not really. I'm going to have this much, which is a very small number. So, did I need to do all this math? No, I showed you this math once. So now what you can do is simply look at the difference in the pKa's of the acid, right? So the first thing we said was pKa 33 versus pKa 15. What that tells you is that it's biased by 18 orders of magnitude toward the weaker acid. Let's talk about this equilibrium. This comes up actually a lot in organic synthesis for those of us that do that for a living. This is N-butyl lithium. So it actually has a carbon-metal bond here. And like I said before, when you see lithium or sodium or potassium, any of those alkali metals, you can kind of replace that in your head with Li plus and whatever it's bound to minus. N-butyl lithium, we add some amine. pKa is about 35. In equilibrium with just simply the alkane, this thing has now taken a proton. pKa is 48. That is about the highest pKa number you'll see. And over here we have LDA. Once again, we're going to more or less remember that this is N minus Li plus, kind of like a salt. What is our equilibrium constant? Well, we just look at the numbers. So this is pKa 35, this is pKa 48. Which is the stronger acid here? It is the amine. This is a weak acid, and so this is actually a weaker base than this is. How much? I can just take the difference in pKa's. If we want to calculate the Ka, we can do the big derivation that I just did before for the last example. Or we can just say, all right, I remember this from before. I can just take the difference in pKa units. Here, this is favoring the weak acid, and the difference is 13 pKa units. And a pKa unit, remember, is a power of 10. So 13 pKa units is 10 to the 13. So the Ka is about 10 to the 13 here, which means that this is complete, right? So if I mix one equivalent of this and one equivalent of that, once they mix, I should not have any of this left. It should all be quantitatively made into these things.